Welcome to the review of vectors and matrices in the first lesson in linear algebra. In linear algebra, we will be working with vectors and matrices a lot. We will be working with planes, which are defined by vectors, lines, which are defined by vectors, and spaces, which are defined by, you guessed it, vectors, and matrices as well. You can put those vectors in a matrix, and then now we have a plane, line, or space defined by a matrix. But we will also be dealing with various dimensions of vectors as well. We'll need to know what they stand for. We'll need to know what they mean. So what does that mean? Most of the time, most of the vectors that I'm going to introduce to you is going to be 2D vectors. However, they should work with 3D as well. In fact, I'm going to probably make a slide soon. Um, let's say over here that has to do with 3D vectors. 3D vectors exactly the same as 2D vectors, except we have an x, a y, and a z coordinate. So we'll draw the vector like that. But yeah, first the vector has a magnitude and direction. That's what a vector is. The magnitude is the length. Vectors have a length, and the direction is where it's pointing, right? So a vector that's like this and a vector that's like this are very different vectors because they don't have the same magnitude. So they're not the same vector. We usually write these vectors in component form, not magnitude and direction. Of course, we can do magnitude and direction, but we're going to write it in component form usually. It can be written as 3, 4 like this, or it can also be written as 3, 4 with parentheses, or it can be written 3, 4 like this, or it can be written as 3, 4 like this. Now, this isn't the fourth option isn't really used often, and some textbook may say that this is even wrong. It's even wrong to do this. So the more useful method, the more useful or the more common things that you'll see is with parentheses, which I mean, it looks like a point, but it's a vector in linear algebra. So weird. I like these angular brackets more. I use those in Calc 3. But this is what I'm going to be using the most for this course right here, is the vertical notation for the component form. X is on top, Y is at the bottom or in the middle if it's 3D, and Z is at the bottom if it's 3D. Now, the same vector can be written with magnitude and direction. Of course, if you guys know, we're going to be touching more on that later, but the magnitude can be calculated just using the Pythagorean theorem. As you can see, there's a right angle right here, so if you want to find the magnitude of this, it's just 3 squared plus 4 squared equals 5 squared, right? Just take all the components and then square them and add them together. Take the square root of the answer, and that's what you get for the magnitude. I'm going pretty fast right now because I'm going to be reviewing this a little bit more. The direction is the inverse tangent of um, the ratio between y and x. So um, the direction is actually this angle right here. This angle right here, and it can be determined by, well, tan of this angle is 4 over 3. So the angle is inverse tan, arctan of 4 over 3 radians. Of course, you'll have to do a little bit of a weirder kind of calculation because arctan doesn't have a big domain or a domain it covers the entirety of the unit circle. So if it's pointing this way, you'll have to do a little bit of a weird calculation to try to figure out what that angle is. But that's not very important. That's just to let you know what a vector is. The component form is the most important thing. So we're going to write these vectors in component form. So the component form um, is basically just how much did it move in the x direction, how much did it move in the y direction. And if it's 3D, how much did it move in the z? So what is this? This is, well, it moved 2 in the x direction and 1 in the y direction. So the vector is 2, 1. How about this? How much did it move in the x direction? Uh it moved 1, 2, 3, 4, but not in the x direction. It's in the negative x direction, or -4 in the x direction. It moved 4 to the left. And how much did it move in the y direction? It moved 1, 2, 3, 4, 5, 6 in the negative y direction. So it's -4 on x, negative 6 on y. That is 4 left and 6 down. So the component form is -4, -6. Very simple writing in component form. Notice that it doesn't have to be in the center. It doesn't have to start in the origin. It can, the what do you call it? The initial point, which is what this is called, and the terminal point. Well, first of all, the terminal point doesn't have to be. The terminal point is not the component form of the vector. The component form is always the terminal point minus the initial point. So in this case, it's the terminal point, which is -3 minus 2, -3 minus 2, minus the initial point, which is what? Which is 1, 4. So if you take the terminal point minus the initial point, you'll get -4, -6. And that's the vector. Um, it's probably not that important in this course to know this. It's more important to know it in Calc 3, in multivariable calculus, but suggest you uh, I suggest you at least know how to count the steps so you can know the component form of the vector. And you should also know that the initial point does not have to be in the center, and the any one of those points is not necessarily, or the terminal point is not necessarily the component form, right? It's definitely not the component form in some cases. Um, it's only the component form. The terminal point is only the component form when the initial point is in the at the origin, because you're subtracting 0, 0. So that's the danger that you don't want to get into, is thinking that the terminal point is the component form for every vector. It's not. And vectors don't have to start in the origin. So something you can do with operations with vectors, you can add and subtract the vectors. And the most common way to add and subtract vectors is just to add them horizontally. So you add the 1 that v is contributing and the 2 that w is contributing to the x direction. You get 1 plus 2, which is 3. And you add the 2 in the y direction, v is contributing, -1 that w is contributing. 2 plus -1 is 1. So what does that mean? That means, first of all, what does tip to tail calculation mean? So you take your first vector, you put it at 0, 0. You put the initial point at 0, 0. This is called a position vector, because the vector is pointing at the position of the terminal point. Those are very useful, but we won't use them all the time, but we will use them most of the time. So yeah, the vector is pointing at the position of the point, and you take that tip of v and you attach the tail of w on the tip of v, and then you continue. So v plus w is v from the tail, from tip, I guess you could say tail to tip. I don't know why it's called tip to tail, actually. This looks more like a tail to me, and this looks more like a tip to me. I don't, it should be tail to tip, but it's tip to tail for some reason. But you attach the non-arrow part of W to the arrow of V, and once you make that V and W, the v plus w will be the initial point of v to the terminal point of w. Um, Basically close to make it a triangle. But the initial point has to start from the origin because v started from the origin, and then it has to end at the tip of w. So that's v plus w right there. So geometrically, it also makes sense because if you move 1 and then move 2, you'll end up with 3, and then if you move up 2 and then move down 1, you'll end up with 1. So that's v plus w. Now what about v minus w? So in fact, with v minus w, when you multiply by a negative number, negative 1, they change direction. They change it to the complete opposite direction, so it points the other way around. Now I'm gonna say this is multiplied by a negative number, not a scalar. We'll talk about scalars later. Scalars are not negative numbers. They're actually any number. So if you take v right here, and if we were to do v plus w, we would do v plus w, which would make our vector like this. That's v plus w, but it's not. We're doing v plus negative w. So v plus negative w. Since negative w is our new vector that we want, the tail of negative w starts at v, and then the tip of negative w, or the arrow part of the negative w, is where v minus w needs to go to. So v minus w will be from the origin, so that's where v starts, to the tail of negative w, or the arrow part of negative w, and that will get you, instead of it'll get you 1 2, and then we're moving negative 2 now, so 1 minus 2 is negative 1, and then v moved 2 up, but since it's moving the opposite direction now, we're moving 1 more up, so it's negative 1 and 3. And that's it. That is the addition and subtraction. Multiplication works a little bit different. Let's do the examples first. So v plus w with these, you don't have to draw them out tip to tail. I'm not going to because that'll take too long. 1 plus v plus w is 1 4 plus 2 5, and if you add horizontally, you will get, say it with me, 3 2 1 3 9 3 9. And v plus u, simple as well. 1 4 plus 0 negative 1, which is equal to 1 3. And u minus w is 0 negative 1 minus 2 5. So with subtraction, you also just subtract horizontally. Negative 2 negative 6. And I don't, this is just a coincidence, but they're all multiples of each other. Like, do you notice they're all multiples of each other? That was completely coincidental. I did not. Maybe my brain is wired like that I see patterns like that just unconsciously, but I did not plan to make this lesson so that they were just multiples of each other. But that's quite cool, I guess. Anyways, scalar multiplication. What's scalar multiplication? Scalar multiplication is when you multiply a vector by a number, by a scalar. It's not a vector. So it's not vector times vector, but it's vector times number. And the number is called the scalar. It scales the vector by an amount. That's why it's called a scalar, because it scales the vector. It makes it bigger by a certain amount, 2 in this case, and negative 3 in this case. Negative 1, negative v means it goes the opposite direction, so negative 3v means it's 3 times bigger and goes the opposite direction. So that's just scalar multiplication. You multiply all the components by the scalar. Simple. All right, let's evaluate. So 3v is 3 times 1, 4, and this is it looks kind of like the distributive property, and you wouldn't be wrong if you said it was distributive property. It's just 3, 12. 3, 12. 3 times 1, 3 times 4. What's 4w? 4w is 4 times 2, 5, and then minus 2 times u, so 0 minus 1. So what's 4 times 2? 5 is 8, 20. And then minus 2 times minus 1 is minus 0 minus 2. You can multiply by negative 2 and then just do a plus. That's probably better. But I'm just going to do this. So 820 minus 0 negative 2 is 822. 8 minus 0 and then 20 minus negative 2. 4 times v plus w minus u. So what's v plus w minus u? 4 times v, 1, 4, plus w, 2, 5, minus u, minus 0, negative 1. So yeah, let's add. 1 plus 2 is 3. In fact, I can just get rid of the parentheses, 3. 4 plus 5 is 9, minus negative 1 is 10. So 4 times that is 4 times 3, 12. 4 times 10, 40. 1 half u minus 1 fourth v. What's 1 half u? 1 half u is 1 half times 0, negative 1, minus 1 fourth v, 1 fourth, 1, 4. This is not, this is just not 1 times 1 and then 4 times 4. It's 1 fourth times 1 and 1 fourth times 4. What is this? This is equal to 0 and negative 1 half. And then minus 1 fourth. I'm gonna do it the other way. I'm not gonna multiply just 1 fourth to 1 and 4, but I'm gonna multiply the entire scalar of negative 1 fourth. So then I'll end up getting plus negative 1 fourth and negative 1, which will give me what? Which will give me minus 1 fourth minus 3 halves. Right. All right. So this blank page for 3D vectors. So 3D vectors have 3 components. The plane or the space that they are located in is called R3, which is 3-dimensional space. And it's covered by XY plane. This is X, this is Y, this is Z. Every time. Has to be like that. X, Y, and Z. It can also be X, Y, and Z, but that's just rotating it a little bit. It's okay. But it has to be like this, where the X is on the left-hand side of Y, because of something called the right-hand rule. If you want more, if you want more info on that, check the video on multivariable calculus, cross product, I think, 1.2. But yeah, this is X, Y, and Z. And if we wanted to draw a vector like 1, 2, 3, that will be a little bit hard to draw. We'll just take 1, we'll take 2, and then we'll kind of like make a projection. This has to be like a little bit slanted now because our X coordinate's a little bit slanted. So I'm going to make it a little bit slanted. And then 1, 2, 3. So, and then I guess you could also make a copy here. 1, 2, 3. So it starts right here and it ends right here. There you go. So that's 1, 2, and 3. It's basically just the point 1, 2, 3 in the 3D space. But it's a vector instead. It starts at 0, 0, and then it ends at 1, 2, 3. It doesn't have to start at 0, 0. It can start anywhere, but it has to travel 1 in the x direction, 2 in the y direction, and 3 in the z direction. I was just drawing a position vector because position vectors are easy to draw. I can just start from 0, 0, 0, 0, 0, 0, and that's easy to easier to draw than having it float in space somewhere else. So yeah, these are vectors in 3D space, and they work the exact same. They have a magnitude and direction as well. Their direction is not really clearly defined. The direction is not defined by like tan inverse. It can be defined by something called direction cosines, but I'm not going to get into those. The direction is the component form, basically. Because 1, 2, 3, there's only kind of one subset of vectors that can point in the direction of 1, 2, 3, and that's any multiple of 1, 2, 3. So the direction is the vector itself. In fact, if you want to get like pure direction, you can make it a unit vector by taking the vector and then dividing it by its magnitude. But I'm not going to get into those. That's not important to know until later. What is important to know is how to add vectors in 3D space. Tip to tail still works. So if you had v is equal to 1, 3, 5, and u is equal to -1, -2, -3, and then you were asked to find 3v minus 2u, what would that be? That would be 3 times 135 minus 2 times -1, -2, -3, which would be 3, 9, 15. 3, 9, 15 plus 2, 4, 6, which is 5, 13, 21. So it still works the exact same. You multiply by every component and you add horizontally. Same method to add and subtract and multiply vectors. Now, what are matrices? Matrices, you probably first saw them in algebra. They are, or algebra 2. They are pretty strange. They look pretty strange. They look pretty foreign. But we're gonna work with them a lot, and I'm gonna teach you not to be scared of them because they can actually do some pretty neat stuff. For example, elimination. For example, um, column space, null space. They can do a lot of stuff. Diagonalization, symmetric, transpose. Yeah, very, very, very neat stuff. You don't have to be scared of them, and we'll learn them inside out. So, matrices, you can do some things with matrices. They are just like a storage unit for numbers, just like a hard disk for numbers, but you actually get to see all the numbers. So there are certain things you can do with matrices. I'm gonna show you two things right here that you can do with matrices. So you can do. I'm gonna go with the bottom first because that's what we've been talking about. Vectors. The bottom, we're storing the component forms of two matrices. So in v1 we're doing -1 and -2, so that's the first vector right here, -1, -2, and then for v2 we're doing 3, 1. That's the second vector, 3, 1. So we literally just slot them into the corresponding columns. We made an extra column for the second vector, and now it becomes a matrix. In fact, all vectors are matrices if they're written in this form. This is a oh, wait, give me a minute. These are matrices. Matrices. They are just a 2 by 1 matrix. There's only one column for them, so we read them off as vectors, but they're actually matrices as well. They're just a special type of matrix because they only have one column. So 2 by 1. We read that type of notation by number of rows and number of columns. So this is a 2 by 2. This is a 3 by 3. Um, these are all 2 by 2s. This is a 3 by 1, not a 1 by 3. It's a 3 by 1 because there's 3 rows, or well, 3 numbers, but 3 rows and only one column. So that's a 3 by 1 matrix. So yeah, those are two vectors put into a matrix. What else can we do? We can also model equations. So you'll learn how to multiply matrices later, but we can store all the coefficients in this matrix. We can store all the variables in this matrix, right? Which represents the situation right here. Then we can say that's equal to all of the answers, all of the constants in this matrix. So these three matrices just modeled this entire systems of equations right here. So those are some things that you could do with matrices. And adding, subtracting, and multiplying them by a scalar is the exact same. So let's try to do that right now. So what's a plus c? A, oh yeah, so side note, matrices, we usually use capital letters for them. Not bolded, capital, that would be weird. Matrices, we use capital letters. Vectors, we use either bolded or with the arrow. So that's why I have v1 with the arrow, v2 with the arrow. So, sometimes you'll see ax is equal to b. You'll see this later on in the course. That is a matrix times a vector is equal to a vector. Matrix times a vector equals a vector. Right? So capital letters usually represent matrices. Pretty much nearly always represents matrices in this class. And X and B, the stuff with the arrow on top of them or bolded, they are vectors. So a plus c is 1, 4, 2, 3 plus 2, 0, 0, 1. I'm not gonna write them out. I'm not gonna show my work. I'm just say, well, 1 plus 2. So it's instead of like just horizontally, it's by position. So this is the first column, first row, and this is the first column, first row. So 1 plus 2 is 3. First column, second row, first column, second row, and second column, second row, second column, second row. So just add the corresponding positions. 4 plus 0 is 4, 2 plus 0 is 2, 3 plus 1 is 4. B minus 2c. What's minus 2c? Let's work out minus 2c first. So you multiply everything by minus 2. That's minus 4, minus 2, 0, 0. So that's minus 2c, so we can take b. And then minus b, and then plus minus 2c. That's minus 4 plus minus 4 is minus 8. Minus 5 plus 0 is minus 5. 7 plus 0 is 7. And then 8 plus minus 2 is 6. So that is your matrix for b minus 2c. And then minus 2 times a minus b minus c. What does that mean? So a minus b minus c is you take the negative of b, which is just you flip the signs of b basically. Negative 4, negative 5, 7, and 8. If you flip the signs, you will get. I'm actually going to show all my work now. So negative 2, 1, 4, 2, 3, and then plus negative 4, negative 5. So negative b is 4, 5, negative 7, negative 8, and negative c is negative 2, 0, negative 2, 0, 0, negative 1. So what's this equal to? This is equal to negative 2 times, let me move this up a little bit. There we go. Negative 2 times 1 plus 4 plus negative 2 is 3. 4 plus 5 plus 0 is 9. 2 minus 7 is minus 5. And 3 minus 8 minus 1 is minus 6. So negative 2 times that, which is equal to negative 6, negative 18, positive 10, positive 12. And that's how you multiply matrices. And that's going to be it for the review. We will start with our real lesson, 1.1, later on in this week. I will see you guys for that lesson.